Hello, friend. Welcome back to another quiet journey through the cosmos. Some nights the sky feels deeper than it should, stars breathe slower, silence stretches wider, and somewhere far beyond what eyes can see, something impossibly bright is burning. It has been burning for billions of years. It will burn long after we're gone. And for decades, no one knew what it was. Tonight we're drifting toward a mystery that rewrote the universe. A single point of light, brighter than 1 trillion suns, smaller than a solar system. It shouldn't exist, but it does. And finding it changed everything we thought we knew about the cosmos. Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's drift. Imagine standing in a field at night. No city lights, no moon, just stars scattered like salt across black velvet. Your eyes adjust. You start to see more. Faint stars, distant stars. Stars so far away their light has traveled for millions of years just to reach you. And then, if you had the right telescope, the right moment, the right patch of sky, you might see it. A tiny dot, unremarkable at first, just another star among billions. But look closer, measure its light, trace its origin, and you'll find something that doesn't belong, something that shouldn't be possible. This is 3C273, the first quasar ever found, a cosmic lighthouse burning at the edge of forever. It sits roughly 2.4 billion light years away. That distance is almost incomprehensible. If you could travel at the speed of light, the fastest thing in the universe, it would still take you 2.4 billion years to reach it. By the time its light arrives here on Earth in our telescopes, it's already ancient. A ghost. An echo from a time when Earth was still a molten baby, when life was just beginning to stir in shallow seas. But here's what makes it strange. Here's what stopped astronomers cold when they first saw it. Despite being so unimaginably far away, 3C273 is one of the brightest objects in the entire sky. Not to the naked eye, of course, but through a telescope, it blazes. It outshines entire galaxies. It radiates more energy in a single second than our sun will produce in its entire 10 billion year lifetime. Think about that for a moment. More light than 1 trillion suns, from a region smaller than our solar system. How is that possible? For a long time, no one knew. Scientists stared at the data. They checked their instruments. They recalculated. They wondered if maybe they'd made a mistake, because nothing in the known universe could be that bright and that small at the same time. Stars couldn't do it. Galaxies couldn't do it. Supernovae, the explosive deaths of massive stars, could do it, but only for a few weeks. 3C273 had been shining steadily for millions of years, possibly billions. It was like finding a candle flame visible from across an ocean. Impossible. Yet there it was. The name itself is humble, almost boring. 3C273. It sounds like a catalog number because that's exactly what it is. The third Cambridge catalog of radio sources object, number 273. In the 1950s and 60s, astronomers were just beginning to map the radio sky. They built huge dishes, metal ears, listening to the whispers of the cosmos. Most stars are quiet in radio waves, but some objects scream. 3C273 was one of them, a powerful radio source. Loud, persistent, strange. At first they thought it might be a star within our own galaxy. Just something unusual, maybe a strange type of variable star, something we hadn't cataloged yet. But when they finally got a good optical image, when they pointed a traditional telescope at it and really looked, they saw something baffling, a blue star-like point, and stretching away from it a faint jet. A stream of light like a cosmic contrail extending outward into the void. That jet was the first clue. Stars don't have jets, not like that. In 1963, A Dutch-American astronomer named Martin Schmidt was studying 3C273 at the Mount Palomar Observatory in California. He was trying to understand its spectrum, the fingerprint of light that reveals what something is made of and how fast it's moving. He looked at the lines in the spectrum. They didn't make sense. The patterns were familiar hydrogen and other elements, but they were shifted, displaced, pushed toward the red end of the spectrum. Redshift. A sign that something is moving away from us. Fast. Schmidt did the math, and what he found shook him. The redshift of 3C273 was enormous. It was receding from Earth at roughly 47,000 kilometers per second. That's about 16% the speed of light. And according to Hubble's law, the relationship between distance and velocity in an expanding universe that meant 3C273 wasn't nearby at all. It was billions of light years away. If it was that far away and still that bright, then it had to be radiating an unfathomable amount of energy. More than anything humanity had ever observed. Schmidt later said he couldn't sleep that night. The implications were too vast, too strange. He had found something that shouldn't exist, a cosmic anomaly, a tear in the fabric of what was supposed to be possible. Other astronomers began checking the data. They found more objects like it, dozens, then hundreds, distant, bright, impossibly energetic. They called them quasi-stellar radio sources, quasars for short, stars that weren't stars, lights that defied reason. And 3C273 was the first, the Rosetta Stone, the key that unlocked an entirely new chapter in our understanding of the universe. But understanding what it was that took longer, much longer. Because to explain 3C273 scientists had to accept something even stranger, something lurking at its heart, something invisible, something that bends space, devours stars, and turns matter into pure radiant energy. A supermassive black hole. Not just any black hole, a monster. Hundreds of millions of times more massive than our sun, spinning, feeding, glowing. Not because it emits light, black holes don't, but because everything falling into it heats up to millions of degrees and screams its last light into the void before vanishing forever. The light we see from 3C273 isn't the black hole itself. It's the funeral pyre of everything it consumes. Gas, dust, stars, all spiraling inward faster and faster, hotter and hotter, until they shine brighter than galaxies. And that jet, the strange stream of light stretching outward, that's matter and energy being flung away at nearly the speed of light. Particles accelerated to unimaginable speeds, shot out into space like a cosmic blowtorch. The jet from 3C273 stretches over 200,000 light years. Longer than our entire Milky Way galaxy is wide. It's violent. It's beautiful. It's a glimpse into the chaotic heart of the universe. When you look at 3C273, you're not just seeing light, you're seeing time. You're seeing the universe as it was 2.4 billion years ago. Back then, Earth was unrecognizable. No trees, no animals, just single-celled life quietly evolving in ancient oceans. And across the universe, this quasar was already blazing, already pouring light into the void, light that would travel for eons, crossing unimaginable distances until one night it would fall softly onto a telescope mirror in California, and a man would see it and everything would change. We think of the night sky as permanent, fixed, eternal, but it's not. It's a gallery of ghosts. Every star you see is a time capsule. The light from our sun takes 8 minutes to reach us. When you feel its warmth on your face, you're feeling the past. The nearest star beyond the sun, Proxima Centauri, is 4.2 light years away. When you see it twinkle, you're seeing it as it was 4 years ago. And 3C273. You're seeing it as it was long before humans ever walked upright, before our ancestors, before mammals ruled the earth. The universe is a museum of lost time, and 3C273 is one of its oldest exhibits. It's still out there, right now, still shining, still feeding, still pouring light into the cosmos. By the time that light reaches Earth, we might be gone. Our civilization might be dust, but the light will keep coming, patient, tireless, indifferent. There's something humbling about that, something quietly magnificent. We are small, brief, flickering. But we looked up, we measured, we wondered, and we found something impossible. We gave it a name, we told its story. And that story, that search for understanding it, didn't end with 3C273. It only began there, because once we knew what to look for, we found more, thousands more. Quasars scattered across the universe like embers from a fire we're only beginning to understand. Some even farther, some even brighter, some from a time when the universe itself was still young, still wild, still forming its first galaxies. But none of them were the first. That honor belongs to 3C273, the lighthouse, the anomaly, the question mark written in light. You don't need to understand everything tonight. Just rest. Just let the wonder settle softly. Let the mystery breathe. Because that's what science is really. Not answers, not certainty, just the quiet courage to keep looking, to keep asking. Even when the universe answers back with something impossible, and 3C273 was impossible until it wasn't. Until we learned to see, until we learned that the cosmos is stranger, wilder, and more brilliant than we ever dared imagine. So, how did we find it? How did a single dot of light in a photograph become the key to understanding the most violent, energetic phenomena in the universe? That's where the story really begins. The late 1950s were a strange time for astronomy. The universe was getting louder, not louder in the way you might think, not sound, but radio waves, invisible whispers from deep space flooding Earth's atmosphere waiting to be heard. And scientists had just learned how to listen. Before radio telescopes, we saw the universe only in visible light. Stars, galaxies, nebulae. Beautiful, yes, but incomplete, like watching a symphony through a soundproof window. You see the musicians move, but you miss half the story. Radio astronomy changed that. It opened a new window, a new sense. And what poured through was strange, unexpected, often baffling. In 1959, astronomers at Cambridge University in England published something called the Third Cambridge Catalogue of Radio Sources, the 3C Catalog for short. It was a list, a census of the radio sky, 471 objects that glowed brightly in radio wavelengths. Most of them were distant galaxies. Some were supernova remnants, others no one could quite explain. Object number 273 caught attention early, 3C273. It was bright, very bright. One of the strongest radio sources in the sky. But when they tried to match it to something visible, something they could see with an optical telescope, they ran into trouble. It looked like a star, just a faint bluish star. Ordinary, unremarkable. The kind of thing you'd glance past without a second thought. But stars aren't supposed to emit strong radio waves. Most stars are radio quiet. Our sun produces some radio noise, but it's faint, barely a whisper, nothing like what 3C273 was broadcasting. So astronomers were confused. Was it a star? Was it something else pretending to be a star? Or had they made a mistake in matching the radio position to the optical object? For years it sat in the catalog, unresolved, a puzzle waiting for the right person, the right instrument, the right moment. That moment came in 1962. The moon in its slow orbit around Earth occasionally passes in front of distant objects. We call these events occultations, and they're useful, very useful. Because if you watch carefully, you can see exactly when an object disappears behind the moon's edge and exactly when it reappears. That gives you a precise position. Down to the arc second. No ambiguity. On August 5, 1962, the moon occulted 3C273. Cyril Hoazard, an astronomer working at Parkes Observatory in Australia, watched it happen. He timed it. He measured it. And for the first time, humanity knew exactly where 3C273 was. Not approximately, exactly. Armed with that precise position, astronomers pointed optical telescopes at the right spot. And they saw it clearly, a 13th magnitude blue star, still faint, still unremarkable to the eye. But now they knew for certain. This was the source. This little dot of light was screaming in radio waves. Photographs were taken, plates were developed, and in those images someone noticed something odd, a faint wisp extending from the star. A jet, a luminous thread stretching away into space. Stars don't have jets. Planets don't have jets. Galaxies sometimes have jets, but this didn't look like a galaxy. It looked like a point, compact, singular. The images were sent to Martin Schmidt at the Mount Palomar Observatory in California. Schmidt was a spectroscopist. His job was to split light into its component colors to read the chemical fingerprints hidden in starlight. Every element emits light at specific wavelengths. Hydrogen has its signature. Helium has its own. Carbon, oxygen, nitrogen, all of them leave marks. And by reading those marks, you can tell what something is made of. Schmidt pointed Palomar's 200-inch telescope at 3C273 and captured its spectrum. He expected something ordinary, maybe a hot star, maybe something with unusual composition. But what he saw didn't match anything familiar. The lines were there. He recognized the pattern. It was hydrogen. But the wavelengths were wrong, shifted, stretched toward the red end of the spectrum. He checked his calibration. He rechecked the math. He stared at the spectrum for hours. And then it clicked. The lines weren't wrong. They were red-shifted, Doppler shifted. The same effect that makes an ambulance siren drop in pitch as it speeds away from you. Light does the same thing. If an object is moving away from you fast enough, its light stretches. Blue becomes red. Frequencies drop. The redshift of 3C273 was 0.158. That might sound small. It's not. In the language of cosmology, it's enormous. It meant 3C273 was receding from Earth at roughly 16% the speed of light, 47,000 kilometers per second, fast enough to circle the Earth more than once every second. And if it was moving that fast, if the expansion of the universe had carried it that far, then according to Hubble's law, it had to be incredibly distant. Schmidt calculated the distance, 2.4 billion light years. Roughly, he sat back. He felt the weight of it. Because if 3C273 was that far away and still visible from Earth, still bright enough to photograph, then it had to be extraordinarily luminous, not star bright, not galaxy bright. Something else entirely. Something that radiated more energy than anything known to science. Schmidt published his findings in the 1963. The paper was short, modest, almost understated, but its implications were vast. He had found something that didn't fit into any existing category. It wasn't a star. It wasn't a galaxy. It was quasi-stellar, star-like, but not a star. Other astronomers scrambled to check. They found more. Within months, dozens of similar objects were identified, all distant, all incredibly bright, all defying explanation. Jesse Greenstein and Thomas Matthews found another 13C48 with an even higher redshift. Alan Sandage found more. The floodgates opened, they needed a name. Quasi-stellar radio source was too long, too clunky. Someone shortened it. Quasar. The term stuck. And 3C273 became the first quasar ever confirmed. But confirmation didn't mean understanding. No one knew what quasars were. No one knew how they worked. Stars couldn't produce that much energy. Galaxies could, but galaxies were extended fuzzy spread out. Quasars were points, compact, almost star-like in appearance. Some scientists propose they were nearby, objects may be ejected from our galaxy at high speed. That would explain the redshift without requiring them to be distant. But the numbers didn't add up. The energy required to accelerate something to 16% light speed was absurd. And if they were nearby, we should see more of them. We should see them moving across the sky. We didn't. Others suggested they were optical illusions, gravitational lensing. Light from distant galaxies bent and magnified by foreground mass, but lensing produces multiple images, arcs, rings. 3C273 was a single point. The most radical idea, the one that eventually proved correct, was also the hardest to accept. Quasars were real, they were distant, and they were powered by something so extreme, so violent, that it made supernovae look dim by comparison. What could do that? What engine could turn matter into light with such ferocious efficiency? The answer was waiting, lurking in Einstein's equations, predicted decades earlier but never observed, never confirmed. Black holes, not small black holes, not stellar mass black holes formed from the collapse of single stars. Those were known at least theoretically, but something far larger, millions of times more massive, supermassive black holes, monsters sitting at the centers of galaxies feeding on gas and stars converting mass into radiation with brutal elegance. In the early 1960s, this was science fiction. Black holes themselves were still controversial. Many physicists doubted they existed at all. They were mathematical curiosities, solutions to equations, not real objects you could find in the sky. But 3C273 changed that. It forced the issue, because nothing else fit. Nothing else could explain the brightness, the compactness, the sheer power. Only a black hole millions of times more massive than the sun could produce that kind of energy. Only something so dense that space itself bent around it, where gravity became so strong that not even light could escape, could generate the radiation we were seeing. It took years for the theory to solidify, for models to be built, for the math to be worked out. But slowly, piece by piece, the picture emerged. 3C273 wasn't a star. It wasn't even a galaxy, not in the traditional sense. It was a galaxy with a monster at its heart, a supermassive black hole feeding, growing, shining. And we had stumbled across it by accident, by listening to the radio sky, by watching the moon pass in front of a faint blue dot, by refusing to accept the easy answer. Martin Schmidt later said that discovering 3C273's redshift was one of the most exciting moments of his career. But it was also terrifying, because it meant the universe was stranger than anyone had imagined, brighter, more violent, more mysterious. He was right to feel that way, because 3C273 was just the beginning, just the first crack in a door we didn't know existed, and once that door opened, we couldn't close it. We could only step through, into a cosmos filled with quasars, thousands of them, millions of them, each one a beacon, each one a mystery, each one a lighthouse burning at the edge of forever. The star that wasn't a star had revealed something profound. The universe wasn't static, it wasn't gentle, it was alive with energy, alive with chaos, and we were only just beginning to see it clearly. But seeing it was one thing, understanding it was another. Because even after we knew 3C273 was distant, even after we knew it was impossibly bright, one question remained. A question that haunted astronomers for years. A question that demanded an answer. How? How does something smaller than a solar system outshine 100 billion stars? That's the question that haunted astronomers after Martin Schmidt's discovery. They had the distance. They had the measurements. They could calculate the luminosity, the total energy output with reasonable precision, and the numbers made no sense. 3C273 was producing roughly 4 trillion times more light than our sun. 4 trillion, not 400, not 4,000. 4 trillion. To put that in perspective, imagine every star in the Milky Way galaxy suddenly doubling its brightness, then tripling it, then multiplying it by 40. You'd still fall short of what 3C273 was doing. And it was doing it from a region so compact that if you could somehow place it where our solar system is, it might not even extend past the orbit of Neptune. How is that possible? What mechanism in nature allows something so small to be so catastrophically bright? Let's pause for a moment and consider what brightness really means. When we say something is bright, we're measuring luminosity, energy radiated per second. Our sun puts out about 3.8 times 10 to the 26th watts. That's a lot. It's enough to warm an entire planet from 93 million miles away. Enough to sustain life. Enough to drive weather systems, ocean currents, photosynthesis. The sun is not a dim bulb, but 3C273 makes the sun look like a dying ember. If you took 3C273 and placed it 33 light years away, roughly the distance to the star Vega, it would appear as bright as the sun does from Earth. You could get a sunburn from it. You could read a book under its light at midnight, from 33 light years away. Now, imagine it at its actual distance, 2.4 billion light years. And it's still visible, still detectable, still flooding our telescopes with photons that have traveled across a quarter of the observable universe just to reach us. The math is dizzying. The implications are unsettling. Because brightness on that scale requires fuel, enormous amounts of fuel, and something has to be converting that fuel into light with terrifying efficiency. Stars do this through nuclear fusion. Hydrogen atoms smash together under immense pressure and heat fusing into helium releasing energy in the process. It's the same reaction that powers hydrogen bombs. But in stars it's slow, controlled. The sun has been burning for 4.6 billion years and will burn for another 5 billion. It's efficient, yes, but not that efficient. Fusion converts only about 0.7% of mass into energy. The rest remains locked in the resulting helium nuclei. To power 3C273 through fusion, you'd need to burn the mass of several suns every single year. And even then you'd run into problems. Fusion happens in cores, dense hot cores. If you tried to cram that much fusion into a solar system-sized region, the radiation pressure would blow it apart. It couldn't hold together. It would explode, not shine steadily for millions of years. Explode. So, fusion doesn't work. What else is there? Supernovae came to mind early on. When a massive star exhausts its fuel and collapses, it releases an enormous burst of energy. For a few weeks, a single supernova can outshine an entire galaxy. Could 3C273 be some kind of continuous supernova, some chain reaction of exploding stars? No. Supernovae are brief, right? Yes, but transient. They flare and fade. 3C273 had been shining steadily since at least the 1950s, probably much longer. Decades, centuries, millennia, possibly millions of years. You can't sustain a supernova for that long. The physics doesn't allow it. Astronomers were running out of options. Every conventional explanation failed. Every known process fell short. And yet, the light kept coming. Steady, relentless, impossible. Then someone did a thought experiment, a dark thought experiment. What if gravity itself was the engine, not fusion? Not chemistry, not explosions, just gravity. Pure, unrelenting gravitational collapse. Einstein's general relativity had predicted something strange decades earlier. If you compress enough mass into a small enough space, gravity becomes so strong that space-time itself warps beyond recognition. The escape velocity exceeds the speed of light. Nothing can get out. Not matter, not light, not information, a black hole. But here's the key insight. Matter doesn't just vanish into a black hole instantly. It spirals inward. It forms an accretion disk, a swirling maelstrom of gas and dust orbiting faster and faster as it falls. And as it orbits, it heats up. Friction, compression, magnetic fields tearing through ionized gas. Temperatures soar into the millions of degrees, and at those temperatures, matter radiates violently. The closer you get to the black hole, the faster you orbit, the hotter you become. Near the event horizon, the point of no return, gas reaches temperatures of 10 million degrees or more, hot enough to emit X-rays, hot enough to shine brighter than any star. And here's the beautiful, terrible part. Gravity is incredibly efficient, far more efficient than fusion. When matter falls into a black hole, up to 40% of its mass can be converted into energy. 40%. Compare that to fusion's 0.7%. It's not even close. A black hole feeding on gas and stars is the most efficient engine in the universe. Nothing else comes close. Nothing. If 3C273 had a supermassive black hole at its core, millions or even hundreds of millions of times more massive than the Sun, and if that black hole was actively feeding devouring material from its surroundings, then yes, it could produce that much light. It could shine brighter than galaxies. It could sustain that brightness for millions of years. As long as there was fuel, it would burn. The theory was elegant, radical, and at the time, almost impossible to prove, because black holes by definition don't emit light. You can't see them directly. You can only see what they do to the space around them. The light from 3C273 wasn't coming from the black hole itself. It was coming from the matter falling into it, the accretion disk, the death spiral. Still, the idea took hold, slowly, reluctantly, because it was the only explanation that worked, the only mechanism that fit the data. And as more quasars were discovered, as their properties were cataloged and compared, the black hole model became harder and harder to ignore. By the 1970s, it was the leading hypothesis. By the 80s, it was consensus. By the 90s, observations from space telescopes like Hubble confirmed it. Almost every large galaxy has a supermassive black hole at its center, including ours. Sagittarius A star, 4 million solar masses. Quiet now, dormant. But once billions of years ago, it might have been bright. It might have been a quasar. 3C273's black hole is estimated to be around 886 million solar masses, nearly a billion suns worth of mass compressed into a region smaller than our solar system. It's hard to visualize. The human mind doesn't handle numbers like that well. But try this. If you could somehow stand at a safe distance and watch 3C273's accretion disk, you'd see a glowing ring of superheated gas spinning at a significant fraction of light speed. You'd see jets of particles shooting outward at nearly light speed, powered by magnetic fields twisted and stretched by the black hole's rotation. You'd see light so intense it would vaporize anything nearby, planets, stars, anything that wandered too close. And in the center, invisible but undeniable, the black hole itself, a point of infinite density. A place where the laws of physics as we understand them break down, where time slows, where space curves so sharply it folds in on itself. It's violent, chaotic, beautiful in a terrible way, like watching a star being eaten alive, because that's exactly what's happening. Stars wander too close. Gas clouds drift inward, dust, debris. Everything within reach gets pulled in, shredded, heated, ionized, and before it vanishes forever, beyond the event horizon, it screams one last burst of light into the void. That's what we're seeing when we look at 3C273, not the black hole, the scream. Have you ever wondered what it would look like if our sun fell into a black hole? It wouldn't explode. It wouldn't freeze. It would stretch. Spaghettified scientists call it. Tidal forces would pull it into a long, thin stream of plasma. And as it spiraled inward, it would heat up, glow brighter, shift from yellow to white to blue, and just before it crossed the event horizon, it would flash, one final brilliant pulse of light, then nothing. Darkness, gone. Now, Multiply that by millions of stars, happening continuously, over millions of years. That's a quasar. That's 3C273. The numbers are staggering, but they're real, verified, measured. 3C273 radiates about 10 to the 40th watts, 10,000 trillion watts. If you could somehow capture all of that energy for a single second, you'd have more power than humanity has used in its entire history. Every light bulb, every car, every factory, every city, every civilization, combined, for all of recorded time. 1 second of 3C273's output would dwarf it all. And it's been doing this for millions of years, possibly longer. We don't know when it turned on. We don't know when or if it will turn off. Quasars aren't eternal. Eventually, they run out of fuel. The black hole consumes everything within reach, and the accretion disk thins. The light dims. The quasar fades. It becomes a quiet, dormant galaxy with a sleeping giant at its heart. But while they burn bright. Brighter than anything. Brighter than seems possible. N3C273 is one of the brightest ever found. It's a paradox wrapped in a mystery. Something impossibly small producing impossibly vast amounts of energy. Something invisible, a black hole creating the brightest beacons in the universe. Something that defies intuition at every turn. And yet, it's real. It's out there, right now, shining, feeding, waiting for us to understand it just a little bit better. But brightness is only part of the story. Because 3C273 doesn't just shine, it moves. Or rather, it throws. It launches matter into space at speeds that should be impossible. And that jet, that luminous thread stretching across the cosmos, holds secrets of its own. Imagine a beam of light so powerful it could cut through galaxies, a stream of matter moving so fast that time itself slows down for the particles inside it, a cosmic blowtorch stretching across distances that dwarf our entire galaxy. That's not science fiction. That's what's happening right now, shooting out from 3C273. The jet was one of the first clues that something strange was going on. Back in the early 1960s, when astronomers first photographed 3C273 with optical telescopes, they saw it, a faint luminous thread extending from the bright central point. At first, they thought it might be an artifact, a scratch on the photographic plate, a processing error, but it appeared in every image, consistent, real, undeniable. It stretched outward for what seemed like an impossible distance. And as imaging technology improved, as telescopes grew larger and more sensitive, the full scale of the jet became clear. It extends roughly 200,000 light-years from the core of 3C273. That's longer than the diameter of our entire Milky Way galaxy. Our galaxy, which contains hundreds of billions of stars, which measures about 100,000 light-years across, would fit inside the length of 3C273's jet twice over. Think about that scale for a moment. A single structure, a continuous stream, longer than galaxies. And it's not static, it's moving, fast. Observations from radio telescopes, optical telescopes, and eventually space-based X-ray observatories revealed something astonishing. The material in the jet is traveling at roughly 99% the speed of light. Not 10%, not 50%, 99%. Just a whisper below the cosmic speed limit. At those velocities, strange things happen. Relativity kicks in, time dilates, distances contract. A particle moving that fast experiences time differently than we do. For us watching from Earth, millions of years pass. For the particle racing through the jet, far less time elapses. It's like the universe itself compresses for them. How do you accelerate matter to those speeds? What force is powerful enough to fling gas and plasma across hundreds of thousands of light years at near-light velocity? The answer lies in the black hole's spin and magnetic fields. When a supermassive black hole feeds when it pulls matter into an accretion disk, It doesn't consume everything. Some of the material, a small fraction, gets caught in the black hole's powerful magnetic fields. These fields twist and spiral, amplified by the rotation of the disk and the black hole itself. And in certain configurations, they act like a particle accelerator, a natural cosmic scale particle accelerator. Matter gets funneled along the magnetic field lines. Charged particles, electrons, protons get pushed, accelerated, squeezed into narrow beams that shoot out perpendicular to the accretion disk. Two beams, actually, one from each pole, like a cosmic lighthouse with two beams instead of one. We see one of three C273's jets because it happens to be pointing roughly in our direction. The other jet shooting out the opposite side is there too, but it's aimed away from us harder to detect fainter. The one we see is bright, partly because of something called relativistic beaming. When a jet of particles moves toward you at near light speed, the light gets compressed, concentrated, boosted in brightness. It's a Doppler effect on steroids. The energy carried by 3C273's jet is staggering. Some estimates suggest it transports as much energy as the total luminosity of several large galaxies. Not the black hole's energy output, just the jet, just the particles being thrown away. And this has been happening for millions of years, possibly tens of millions. Where does all that matter go? It doesn't just vanish. It slams into the surrounding space, into intergalactic gas, into clouds of hydrogen and helium drifting between galaxies. And when it hits, it creates shocks, waves of compressed gas that glow in radio waves and X-rays, hotspots, lobes of emission. The jet from 3C273 plows through space like a bullet through fog, leaving a trail of disturbed glowing gas in its wake. In some quasars, those lobes are enormous. Radio galaxies like Cygnus A have lobes spanning millions of light years. They're some of the largest structures associated with a single object in the entire universe. 3C273's jet is smaller, relatively speaking, but still immense, still powerful, still reshaping the space around it. Have you ever watched a river carve through rock? Over time, water flowing in the same direction wears away stone, creates channels, changes the landscape. The jet from 3C273 does something similar. It carves through intergalactic space. It heats gas. It pushes material aside. It influences star formation in nearby regions. In a very real sense, the jet is terraforming space itself. But here's a question that puzzled astronomers for years. Why a jet? Why doesn't the black hole just consume everything evenly? Why does some material get ejected at near-light speeds while the rest spirals inward and disappears? The answer has to do with angular momentum and magnetic field geometry. When matter falls toward a black hole, it doesn't fall straight in. It has sideways motion. It orbits. And as it orbits, it carries angular momentum with it. You can't destroy angular momentum. It's conserved. So the black hole can't just swallow it directly. Instead, the accretion disk spreads that angular momentum outward, allowing material to lose energy and spiral inward. But magnetic fields complicate things. They thread through the disk. They connect different regions. And under the right conditions, they can extract energy and angular momentum from the inner disk and funnel it into narrow beams along the rotational axis. It's like a valve, a release mechanism. Instead of everything falling in a small percentage gets redirected, focused, launched. The physics is complex. The math involves magnetohydrodynamics, general relativity plasma dynamics. It took decades to model properly. Even now, simulations struggle to capture every detail. But the basic picture is clear. Black holes don't just pull, they also push. They're not cosmic drains. They're cosmic engines, and jets are one of their most dramatic outputs. If you could somehow place a planet in the path of 3C273's jet, what would happen? First, the radiation would be lethal. X-rays and gamma rays would flood the planet's surface, stripping away any atmosphere, sterilizing the ground. Then, the particles themselves would arrive. High-energy electrons and protons moving at 99% light speed. They'd slam into anything solid with enough force to vaporize it. Not melt, not burn, vaporize. Turn rock into plasma. Turn plasma into radiation. Within seconds, the planet would cease to exist. That's the power we're talking about. Not gentle, not subtle, violent, relentless. A cosmic blowtorch that's been burning for millions of years and shows no sign of stopping. And yet, despite all that violence, there's a strange beauty to it. The Hubble Space Telescope has captured images of 3C273's jet. In visible light, it glows a soft blue. In X-rays, it shimmers with high-energy photons. In radio, it stretches and bends, tracing the magnetic fields that guide it. It's one of the most studied structures in extragalactic astronomy. Scientists have watched it for decades, measuring its brightness, tracking knots of emission as they move along the jet, watching the light change over time. And what they've found is that the jet isn't smooth, it's clumpy, lumpy. Knots of brighter emission travel down the jet at apparent speeds that sometimes seem to exceed the speed of light. Not actually faster than light, that's impossible, but it looks that way from our perspective. It's another relativistic illusion. When something moves toward you at near light speed, at a slight angle, geometry and light travel time conspire to make it look faster than it is. These knots might be regions where the jet's density increases temporarily, or where magnetic fields are particularly strong, or where the jet encounters pockets of denser intergalactic gas. Whatever the cause, they light up, they brighten, they move. And by tracking them, astronomers can study the jet's structure, its speed, its evolution. One study in the 1990s tracked a bright knot in 3C273's jet for several years. They watched it move, measured its velocity, and found it was traveling at about 96% the speed of light, projected outward, away from the core, still accelerating possibly even hundreds of thousands of light years from the black hole that birthed it. It's humbling and a little terrifying to realize that nature can build machines like this, engines of pure gravity and magnetism that operate on scales and time scales so vast they dwarf human comprehension. We build rockets, particle accelerators, fusion reactors. Impressive, yes. But 3C273 makes them look like toys, like candles held up to the sun. And the most remarkable part, this isn't unique. Jets are common among quasars, among active galactic nuclei. Thousands of them have been observed. Some are longer, some are brighter, some are pointed directly at us, creating what we call blazars objects, so bright and variable they flicker like cosmic lighthouses. 3C273's jet is just one example, a particularly well-studied example, but one among many. What does that mean? It means the universe is filled with these cosmic flamethrowers, filled with black holes launching jets at near light speed, filled with regions of space being carved and shaped by beams of matter moving faster than anything we can build. It's happening everywhere, all the time, quietly, relentlessly, out there in the dark. And we found it by accident, by looking at a faint blue dot in a photograph, by noticing a wisp of light that shouldn't have been there, by refusing to look away. But the jet is only one piece of the puzzle. To truly understand 3C273, to grasp what's powering it, we need to look at the engine itself, the invisible heart, the supermassive black hole lurking at the center, hidden from view, but impossible to ignore. At the center of all that light hidden behind veils of glowing gas and impossible brightness sits something you cannot see, something that bends space, warps time, devours stars, a supermassive black hole, 886 million times more massive than our sun, and it's hungry. Black holes are strange, deeply strange. They're not objects in the traditional sense. They're regions of space-time where gravity has become so intense that the usual rules break down, where escape becomes impossible, where even light, the fastest thing in the universe, cannot break free. Einstein's equations predicted them in 1915, but for decades most physicists thought they were mathematical curiosities. Interesting on paper, unreal in practice. Karl Schwarzschild, a German physicist serving on the Russian front during World War I, was the first to find an exact solution to Einstein's field equations that describe what we now call a black hole. He did this while stationed in the trenches, surrounded by war, and he sent his results to Einstein, who was both impressed and unsettled. The math worked, but it described something so extreme, so alien, that it seemed nature would never allow it. Schwarzschild died months later from an illness contracted during the war. He never saw his solution become the foundation for understanding some of the most powerful objects in the universe. For years, black holes remained theoretical. Then in the 1960s, as radio astronomy advanced and strange objects like 3C273 were discovered, physicists began to reconsider. Maybe black holes weren't just math. Maybe they were real, and maybe they were the engines powering quasars. The logic was simple, almost elegant. If you want to produce enormous amounts of energy from a small region, you need an incredibly efficient process: nuclear fusion. The power source of stars converts less than 1% of mass into energy. Chemical reactions are even less efficient, but pure gravitational collapse can do much better. When matter falls into a black hole, especially a rapidly spinning one, up to 40% of its rest, mass can be converted into radiation. 40%. It's the most efficient energy conversion process in nature. Here's how it works. Imagine a cloud of gas drifting through space, cold, diffuse, harmless. Then it encounters a supermassive black hole. Gravity pulls it inward. But because the gas has some sideways motion, some angular momentum, it doesn't fall straight in. Instead, it spirals. It forms a disk, an accretion disk. And as the gas orbits closer and closer to the black hole, it speeds up. Faster, hotter, denser. The inner regions of the disk orbit at a significant fraction of the speed of light. Gas clouds slam into each other. Friction heats them. Magnetic fields twist and snap, releasing energy. Temperatures soar into the millions of degrees. And at those temperatures, the disk glows. It radiates across the electromagnetic spectrum: radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. That's the light we see from 3C273, not the black hole itself. The black hole is invisible. But the accretion disk, the swirling vortex of doomed matter spiraling toward oblivion that shines, brighter than galaxies, brighter than anything. Now, 886 million solar masses is almost incomprehensible. Let's try to grasp it. Our sun has a mass of about 2 times 10 to the 30th kilograms. Multiply that by 886 million. The number is so large it loses meaning. But consider this. If you replaced our sun with 3C273's black hole, its event horizon, the point of no return, would extend roughly 2.6 billion kilometers. That's beyond the orbit of Uranus. Neptune would be inside the black hole's gravitational grip. So would Saturn. So would Jupiter. Only the outermost reaches of our solar system would be safe. And that's just the event horizon, the region where the black hole's gravity dominates, where orbits become unstable and matter gets pulled inward, extends much farther, several light years possibly. Entire star systems could orbit a black hole that massive, and some do. At the centers of galaxies, stars orbit supermassive black holes like planets orbit the sun. Our own galaxy, the Milky Way, has one. Sagittarius A star. 4.3 million solar masses. Small compared to 3C273's monster, but still immense. We've watched stars orbit it for decades, tracking their positions year by year. Some of those stars move so fast, their velocities exceed 5,000 kilometers per second. That's nearly 2% the speed of light, and they're held in place by gravity alone. The gravity of an object we cannot see, an object that doesn't emit light, a black hole. In 2020, the Event Horizon Telescope captured the first direct image of a black hole's shadow. Not Sagittarius A star, though they imaged that later. The first was M87 star, the black hole at the center of the galaxy Messier 87. 6.5 billion solar masses, even larger than 3C273s. The image showed a dark circle, the shadow surrounded by a glowing ring of light, the accretion disk. It was proof, direct visual proof that black holes are real. 3C273's black hole hasn't been imaged that way yet. It's farther, smaller in angular size, harder to resolve, but the evidence is overwhelming. The brightness, the compactness, the jet, the variability. Everything points to a supermassive black hole actively feeding, and feeding is the key word. Black holes don't just sit there, they don't suck in everything like cosmic vacuum cleaners. That's a common misconception. If our sun suddenly became a black hole, Earth wouldn't get pulled in. Our orbit wouldn't change. Gravity depends on mass and distance, not on whether the mass is a star or a black hole. We'd keep orbiting. We'd just freeze because the sun would stop shining. Black holes only consume what falls too close, what crosses the event horizon. And for matter to fall in, it needs to lose energy and angular momentum. That happens in the accretion disk. Friction, magnetic fields, turbulence. They drain energy from the orbiting gas, allowing it to spiral inward, slowly, over thousands of years, until finally it crosses the point of no return and vanishes. But before it vanishes, it shines. And the closer it gets, the brighter it becomes. The innermost regions of the accretion disk, the parts orbiting just outside the event horizon, are the hottest and brightest. They emit X-rays, high-energy photons, radiation so intense it would sterilize anything nearby. How much is 3C273's black hole eating estimates vary, but some models suggest it's consuming the equivalent of several solar masses per year, several stars worth of gas and dust every single year. And it's been doing this for millions of years, maybe longer. Where does all that material come from? In the early universe, galaxies were rich in gas. Star formation was rampant, and gas clouds stirred by gravitational interactions. Galactic collisions, stellar winds would occasionally drift inward toward the galactic center, toward the black hole. Over time, that gas would accumulate, form a reservoir, and the black hole would feed on it, slowly, steadily. In 3C273's case, the black hole is likely being fed by its host galaxy. We can't see the galaxy clearly because the quasar is so bright it outshines everything. But it's there, a massive elliptical galaxy probably, with hundreds of billions of stars, and at its heart, the black hole, feeding, growing. Have you ever wondered what happens to matter once it crosses the event horizon? Honestly, we don't know. General relativity predicts that it continues to fall toward the singularity, the point of infinite density at the black hole's center. But near the singularity, space-time curvature becomes infinite. The equations break down. Quantum effects, which we don't fully understand, should become important. Maybe matter doesn't reach a true singularity. Maybe it's transformed into something else. Maybe information is preserved in some way we haven't figured out yet. These are open questions, deep questions, questions that sit at the boundary between physics and philosophy. And 3C273, for all its brightness and violence, can't answer them. Not yet, maybe not ever. But what we can study is the black hole's effect on its surroundings, the way it shapes the accretion disk, the way it launches jets, the way it regulates star formation in the galaxy around it. Because black holes, especially supermassive ones, aren't isolated. They influence entire galaxies. They're connected to galaxy evolution in ways we're only beginning to understand. There's a relationship, a correlation between the mass of a galaxy's central black hole and the mass of the galaxy's bulge, the dense central region of stars. Bigger bulges have bigger black holes. The ratio is remarkably consistent. Roughly 0.1% of the bulge's mass ends up in the black hole. Why, we don't know for sure, but it suggests that black holes and galaxies grow together, co-evolve. Feedback from the black hole from jets and radiation might regulate how much gas can cool and form stars. It's a cosmic thermostat, a balance. If the black hole feeds too aggressively, it heats the surrounding gas so much that star formation shuts down. The galaxy goes quiet. The black hole starves. It dims, becomes dormant. Then over millions of years, gas cools again, drifts inward. The cycle repeats. 3C273 is in the feeding phase, the bright phase, the quasar phase. But this won't last forever. Eventually, the gas will run out, the accretion disk will thin, the light will fade, and 3C273 will become just another quiet galaxy with a dormant black hole at its heart, like most galaxies today, like ours. Quasars were more common in the early universe. Billions of years ago, when galaxies were younger, gas was more abundant, collisions more frequent. The conditions were right for black holes to feed, to grow, to shine. Now most of that gas has been used up, turned into stars, ejected by supernovae. The universe has aged, quieted. Quasars are rarer, but they're not gone. And 3C273 is a reminder, a glimpse into what the universe used to be like, brighter, more violent, more chaotic. A time when black holes ruled, when they carved galaxies with jets of light and reshaped the cosmos. It's humbling to think that something so powerful, so immense, is also invisible, that we can never see it directly. We can only infer its presence, measure its effects, watch the light from matter falling into it. The black hole itself remains hidden. A ghost, a shadow, a question mark at the center of brilliance. And yet, we've learned so much about gravity, about space-time, about the limits of physics, all from studying something we cannot see, something defined by absence, by what it takes away. That's the paradox of black holes. The brightest objects in the universe are powered by the darkest. The most luminous phenomena arise from the most invisible. Light and darkness intertwined, inseparable. And 3C273 taught us that, forced us to confront it, showed us that the universe is stranger, more intricate, more beautiful than we imagined. Because at its heart sits a monster, and that monster impossibly creates light. But 3C273 wasn't alone. Once we knew what to look for, once we understood what quasars were, we started finding them everywhere, thousands of them, scattered across the cosmos, each one a lighthouse, each one a story. And together, they opened a window into the universe's past. One discovery changes everything. One object properly understood can rewrite textbooks, reshape entire fields of study, open doors that no one knew existed. 3C273 did exactly that. It wasn't just a single quasar. It was the first quasar, the template, the key that unlocked a hidden population of objects scattered across the universe waiting to be found. After Martin Schmidt published his findings in 1963, astronomers around the world turned their telescopes toward the sky with new eyes. They started looking at other radio sources from the 3C catalog, other faint blue dots that didn't quite make sense. And they found them. Dozens at first, then hundreds, then thousands. All distant, all impossibly bright, all quasars. 3C48 was confirmed shortly after 3C273. Its redshift was even higher, 0.367. It was receding at roughly 37% the speed of light, farther than 3C273, older, a light from an even more ancient universe. Then came 3C147, 3C 196. The numbers kept climbing, the catalog kept growing, and with each new discovery, the picture became clearer. Quasars weren't rare anomalies, they were everywhere. A vast population of energetic objects, most of them lurking in the distant past. By the 1970s, surveys had cataloged thousands of quasars. By the 1990s, tens of thousands. And today, thanks to digital sky surveys like the Sloan Digital Sky Survey, we've identified over 1 million quasars, 1 million lighthouses scattered across the observable universe, each one powered by a supermassive black hole, each one a window into cosmic history. But here's what's strange. Here's the pattern that emerged as the data accumulated. Most quasars are far away, very far away. The nearest known quasar is still billions of light years distant. There are almost no quasars in the nearby universe. The local cosmic neighborhood is quiet. Galaxies around us, including our own Milky Way, have supermassive black holes at their centers. But those black holes aren't shining. They're dormant, sleeping, starved of fuel. Why? What changed? The answer lies in cosmic time. When we look at distant quasars, we're not just seeing distant objects. We're seeing the past. Light takes time to travel. The light from a quasar 10 billion light years away left that quasar 10 billion years ago. We're seeing it as it was then, not as it is now. And 10 billion years ago, the universe was different. Younger, wilder, richer in gas. In the early universe, galaxies were still forming, merging, colliding. Gas clouds were abundant. Star formation was vigorous. And all that activity fed the central black holes. Material drifted inward. Accretion disks formed. Black holes grew. And they shone. Brilliantly. That was the quasar era. The peak of black hole feeding. Roughly 10 to 12 billion years ago, when the universe was only 2 to 4 billion years old. Since then, things have quieted down. Gas has been consumed, turned into stars, blown away by supernovae and stellar winds. Galaxies have settled, matured. Black holes have run out of fuel. They're still there, still massive, but they're no longer feeding, no longer glowing. The quasar phase for most galaxies has ended. 3C 273 is a holdout, an exception. It's still active, still bright, still feeding. Most quasars at similar distances have long since dimmed, but 3C 273 continues to shine. Why? Perhaps it recently captured a fresh supply of gas. Perhaps a smaller galaxy merged with its host delivering new fuel. Perhaps its geometry, its environment allows it to sustain feeding longer than most. We don't know for certain, but it's remarkable, a relic. A living fossil from an era when quasars dominated the sky. The most distant quasar known as of recent surveys is called J0313-1806. It sits at a redshift of 7.64. That corresponds to a distance of roughly 13.03 billion light years. We're seeing it as it was only 670 million years after the Big Bang. The universe at that time was still an infant. The first stars had just begun to form. The first galaxies were just coalescing. And already there was a supermassive black hole, feeding, shining, creating a quasar. How did black holes grow so massive so quickly? That's one of the great unsolved mysteries in astrophysics. To reach millions or billions of solar masses in such a short time requires either very massive seed black holes to begin with, or incredibly efficient feeding. Maybe both. Theoretical models struggle to explain it. Observations push the boundaries of what we thought possible, and quasars like J0313-1806 are the smoking guns. Proof that the universe, even in its youth, was capable of extremes. Studying distant quasars teaches us about the early universe, about how galaxies formed, how black holes grew, how the intergalactic medium, the gas between galaxies, was heated and ionized. Quasars are cosmic beacons. Their light traveling across billions of years passes through clouds of gas, and those clouds leave fingerprints, absorption lines in the quasar spectrum. By studying those lines, astronomers can map the distribution of matter along the line of sight. They can trace the evolution of hydrogen, helium, heavier elements. They can watch the universe grow up. One famous example is the Lyman alpha forest. When light from a distant quasar passes through neutral hydrogen gas, the hydrogen absorbs light at a specific wavelength, 1,216 angstroms, the Lyman alpha line. But because the universe is expanding, gas clouds at different distances have different redshifts. Each cloud absorbs light at a slightly different wavelength. And when you look at a quasar's spectrum, you see not one absorption line, but a forest of them, hundreds, thousands, each one marking a cloud of hydrogen somewhere between us and the quasar. By analyzing the Lyman alpha forest, scientists can reconstruct the distribution of gas across cosmic time. They can see how structure formed, how the universe transitioned from smooth and uniform to clumpy and complex, how galaxies and clusters emerge from the primordial soup. It's paleontology, cosmic paleontology, using light as the fossil record. And none of this would be possible without quasars, without their brightness, without their distance, without 3C273 showing us they existed. But quasars do more than illuminate the past. They also test physics, general relativity, cosmology, the nature of space-time itself. Because quasars are so distant and so bright, their light can be bent by gravity. Gravitational lensing. When a massive galaxy or galaxy cluster sits between us and a distant quasar, its gravity warps space-time. Light from the quasar bends around the mass, and we see multiple images, or arcs, or rings. Einstein predicted this in 1915. But it wasn't observed until 1979 when astronomers discovered a double quasar, two nearly identical quasars very close together in the sky. Same spectrum, same redshift, but two images. It wasn't two quasars, it was one quasar, lensed by a foreground galaxy. The galaxy's gravity bent the light into two paths, two images. An Einstein cross later showed four images. A quasar quadrupled by lensing. These lensed quasars are powerful tools. They allow us to measure the mass of the lensing galaxy with incredible precision. They let us study the quasar itself in greater detail because the lensing magnifies it. And they provide independent measurements of cosmic distances and the expansion rate of the universe, the Hubble constant. A number that's been surprisingly difficult to pin down. Have you ever thought about how strange it is that we can use gravity to magnify distant objects? That space-time itself acts like a lens. It's one of the most beautiful predictions of general relativity. And quasars, because they're so bright and so far away, are perfect targets for observing it. Quasars also help us understand dark matter, the invisible substance that makes up most of the universe's mass. When light from a quasar passes near a galaxy or cluster, it gets lensed. By measuring how much the light bends, we can infer how much mass is doing the bending, and often the mass is far greater than what we see in stars and gas. That extra mass is dark matter, invisible, detectable only through its gravitational effects, and quasars acting as distant lighthouses reveal its presence. The population of quasars also tells us about galaxy evolution. Because not all galaxies have active quasars, only galaxies with enough gas to feed the central black hole light up. And the conditions for that are specific, often tied to galaxy mergers. When two galaxies collide, their gas clouds collide too. They lose energy. They fall toward the center. They feed the black hole. The black hole brightens. A quasar is born. Most galaxies, including ours, have gone through multiple mergers over their lifetimes. And during those mergers, they probably had quasar phases. periods when the central black hole fed and shone. Then, as the gas was consumed or expelled, the quasar faded, the galaxy settled, became what we see today. Our Milky Way will merge with the Andromeda Galaxy in about 4 billion years. When that happens, gas will be stirred. Some of it will fall inward. Our black hole Sagittarius A star might feed, might brighten, might become a quasar. Not as bright as 3C273, probably, but bright enough to outshine the combined light of billions of stars for a while. Then it too will fade, the cycle will complete, and the merged galaxy will drift quietly through space, its quasar days behind it. It's a humbling thought that our galaxy, our home, might once have been a quasar, that billions of years ago, something like 3C273 might have blazed at the heart of the Milky Way, and that billions of years from now, it might blaze again, briefly, before falling silent once more. Quasars are not eternal. They are phases, episodes in the long, slow life of galaxies. And 3C273, by being the first one we found, by showing us this phenomenon existed, changed how we think about galaxies, about black holes, about cosmic history. Before 3C273, we thought galaxies were gentle, steady, predictable. After 3C273, we realized they were violent, dynamic, capable of extremes, that the universe was once filled with light so intense it dwarfed anything we see today, that black holes, far from being cosmic oddities, were central players in the story of structure formation. And we learned all of this by looking at a faint blue dot in a photograph, by measuring its light, by refusing to accept the easy answer, by following the evidence wherever it led, even when it led to something impossible. That's the power of discovery. One object, properly understood, can change everything. But understanding 3C273 means more than cataloging its properties. It means grappling with what it represents, a message from the past, a signal traveling across time. And the story of that journey, the path its light took to reach us, is as profound as the object itself. Every photon is a time traveler. Every particle of light carries a message from the past. And the light from 3C273 has been traveling for 2.4 billion years. Think about that. 2.4 billion years. The photons arriving at our telescopes tonight left that quasar before dinosaurs walked the Earth, before flowers existed, before complex life crawled onto land. When we look at 3C273, we're not seeing it as it is. We're seeing it as it was, a ghost, an echo from an era so distant it predates most of the history we think of as ancient. And that makes every telescope a time machine, not in the science fiction sense. No spinning wheels or glowing portals, just light, patient light, crossing unimaginable distances at the universe's absolute speed limit, bringing us news from the deep past. Let's walk through what that means. Really sit with it for a moment. 2.4 billion years ago, Earth was a different world. The atmosphere had oxygen, yes. Photosynthesis had been happening for over 1 billion years. Cyanobacteria had transformed the planet, poisoning the early anaerobic life with their toxic waste product oxygen and paving the way for everything that came after. But life was still simple, single-celled, hidden in oceans and shallow pools. There were no trees, no grass, no insects, no animals of any kind. The land was barren, lifeless, a rocky desert under a younger sun. And in the oceans, microscopic creatures drifted, divided, evolved, slowly, so slowly, building the foundation for everything that would come later. But nothing you'd recognize, nothing you could see without a microscope. And while all of that was quietly unfolding on one small planet, orbiting an average star in an unremarkable galaxy 2.4 billion light-years away, a supermassive black hole was feeding, devouring gas and stars, heating an accretion disk to millions of degrees, launching jets of plasma at near-light speed and shining, brighter than 1 trillion suns. Photons streamed outward from that inferno, trillions upon trillions of them. Most disappeared into the void, absorbed by dust, scattered by gas, lost forever. But some, a tiny fraction, set out on a journey across the cosmos, across expanding space, across billions of years. And some of those photons, the lucky ones, the persistent ones, eventually found their way to a small blue planet, where curious beings had built machines to catch them. The light you see when you look at an image of 3C273 is ancient, older than mountains, older than continents, older than most of the rocks beneath your feet. It's been traveling since long before your ancestors existed, since long before anything resembling a human walked upright. And it's only just arriving, now, tonight. That's the strange beauty of astronomy. The night sky is not a snapshot of the present. It's a collage of the past. Every object you see is delayed, time-shifted. The closer the object, the less the delay. But the delay is always there. When you see the moon, you're seeing it as it was 1.3 seconds ago. That's how long light takes to cross the distance between the moon and Earth. Not much, barely noticeable, but real. When you see the sun, you're seeing it as it was 8 minutes and 20 seconds ago. The light that warms your face left the sun's surface over 8 minutes before it touched you. If the sun suddenly vanished, you wouldn't know for 8 minutes. You'd still see it, still feel its warmth. For 8 minutes. Then darkness. The nearest star beyond the Sun Proxima Centauri is 4.24 light-years away. When you look at it, you see it as it was 4.24 years ago. It could have exploded 3 years ago, and you wouldn't know yet. The light from that explosion is still en route, still crossing the void, patient, inevitable. Betelgeuse, the red supergiant in the constellation. Orion is roughly 550 light-years away. When you see it twinkle in the winter sky, you're seeing light that left Betelgeuse in the late 1400s, around the time Leonardo da Vinci was painting, around the time Columbus was sailing. That light has been traveling ever since, crossing space, ignoring empires, ignoring wars, ignoring everything, just traveling. N3C273, 2.4 billion light-years. The light we see left when Earth was still in the Proterozoic eon, when the supercontinent Nuna was beginning to break apart, when the first eukaryotic cells with nuclei were diversifying, when the ancestors of all complex life were just beginning to experiment with new forms. It's dizzying, humbling, to realize that the universe is not a single moment. It's a layered history, a tapestry woven from light arriving at different times from different distances. The farther you look, the deeper you see into the past. And telescopes are not just instruments for seeing far. They're instruments for seeing back, for peering into time itself. Astronomers use this deliberately, intentionally. If you want to study the early universe, you don't need a time machine. You just need a telescope powerful enough to see very distant objects, because those objects, by virtue of their distance, show you the past. Galaxies 10 billion light-years away show you the universe as it was 10 billion years ago, when it was younger, smaller, denser, hotter. That's why the James Webb Space Telescope was built, to look farther, to see fainter, to push deeper into the past than ever before. And what it's finding is astonishing. Galaxies that formed only a few 100 million years after the Big Bang. Stars that shouldn't exist yet, according to some models. Structures that challenge our understanding of how quickly things could form. 3C273, by comparison, is relatively nearby. Only 2.4 billion light-years. Only. That's still deep time. Still far beyond human comprehension. But in cosmic terms, it's almost local. There are quasars 10 times farther. Quasars whose light has been traveling for over 13 billion years. Quasars we see as they were when the universe was barely 5% of its current age. But 3C273 has an advantage. Because it's closer, we can study it in greater detail. We can resolve its jet, measure its variability, track changes over years and decades. Farther quasars are just points of light, faint smudges. 3C273 is bright, clear, accessible, a laboratory for understanding quasar physics. And every observation is an observation of the past. When astronomers measure the brightness of 3C273, they're measuring how bright it was 2.4 billion years ago. When they study its spectrum, they're analyzing light that was emitted before Earth had continents as we know them. It's paleontology, cosmic archaeology, studying the universe not as it is, but as it was. Have you ever wondered what 3C273 looks like right now? Not as we see it, but as it actually is. At this very moment, we can't know. The information hasn't reached us yet. It won't reach us for another 2.4 billion years. By then, Earth will be unrecognizable. The sun will be hotter, brighter. The oceans might be boiling away. Life, if it still exists, will have changed beyond recognition. And the light leaving 3C273 tonight will just be arriving, carrying news of a quasar that might not even be active anymore. That's the tragedy and the beauty of cosmic distances. We're always late, always watching the past, always one step behind. The universe unfolds in real time, but we experience it in delay, like watching a movie where the film is stretched across billions of miles and takes billions of years to reach the projector. But that delay is also a gift, because it means we can see history, we can watch the universe evolve. We can compare nearby galaxies young and active with distant galaxies old and quiet and trace how things change over time. We can study quasars from different eras and see how black hole feeding varied as the universe aged. In a very real sense, the speed of light is finite not as a limitation, but as a feature. If light traveled infinitely fast, we'd only ever see the present. We'd lose access to the past. We'd lose the ability to study cosmic history. The finite speed of light, the delay, the lag gives us a window into time, a way to see what was, and that's invaluable. Some people find this unsettling. The idea that the stars we see might not exist anymore, that the universe we observe is already gone, replaced by something new we won't see for millions or billions of years. But there's another way to think about it. The light is real. It's here, now. Photons that traveled across the cosmos are interacting with atoms in your retina or in a telescope's detector. That interaction is happening in the present. The light may be old, but the act of seeing it is immediate. And the past isn't truly gone, not while its light still travels, not while we can still observe it, study it, learn from it. The past lives on in the light. And as long as we keep looking, as long as we keep building telescopes and asking questions, that past remains accessible, knowable. 3C273 is a monument to that idea, a beacon from an ancient universe, still shining, still teaching us, still reminding us that time and space are woven together in ways that defy intuition. That distance is time, that looking far is looking back, that the cosmos is not a static painting, but an unfolding story, and we're reading it one photon at a time. There's a poetic symmetry to it, that the universe, by being so large, preserves its own history. That light, by traveling so slowly compared to the scale of space, becomes a record, an archive, a living memory of what once was. And 3C273's light, that ancient light, is still arriving. Right now, tonight, as you read this, as you listen. Photons are landing on detectors, being counted, measured, analyzed, each one a messenger from the deep past. Each one carrying information about a black hole, a galaxy, a universe that existed long before we did. It's a conversation across time. We can't speak back. The message is one way, but we can listen. And in listening in, studying and understanding, we honor the journey those photons made. We give meaning to their long voyage. That's what makes 3C273 more than just a bright object in the sky. It's a bridge, a connection between our time and a time unimaginably distant, between our small, brief existence and the vast, ancient universe. And through that bridge, we glimpse something profound, that we are part of this story, that our curiosity, our telescopes, our questions connect us to the cosmos in ways that transcend distance and time. But the story of 3C273 is more than just its light. It's also about what that discovery meant for science, for humanity, for the way we understand our place in the universe. And that legacy, that ripple effect, continues to shape astronomy even now. Sometimes the most important discoveries are the ones that shatter what we thought we knew, the ones that force us to rebuild our understanding from the ground up, the ones that open doors we didn't know existed and reveal landscapes we never imagined. 3C273 was one of those discoveries. It didn't just add a new object to catalogs, it fundamentally changed how we see the universe. Before 1963, before Martin Schmidt looked at that spectrum and realized what he was seeing, the cosmos seemed comprehensible, orderly. We knew about stars, we knew about galaxies, we understood more or less how they worked. The universe had mysteries, certainly, dark corners we hadn't explored, but the framework felt solid, reliable. Then 3C273 arrived, and suddenly nothing was certain anymore. The immediate impact was conceptual. Black holes, which had been mathematical abstractions, theoretical curiosities debated in physics journals, became real, necessary. The only explanation that worked. If quasars existed, and they clearly did, then supermassive black holes had to exist. There was no other way to generate that much energy from such a small region. And if supermassive black holes existed in distant quasars, then they probably existed everywhere, in every large galaxy, including ours. That realization rippled through astronomy. Within a decade, the search was on. Not just for distant quasars, but for evidence of supermassive black holes in nearby galaxies. Dormant ones, quiet ones. Black holes that had finished feeding that no longer shone as quasars but were still there, still massive, still shaping the galaxies around them. In the 1970s and 80s, astronomers began finding them. By studying the motion of stars and gas near galactic centers, they could infer the presence of an enormous unseen mass, something millions or billions of times more massive than the Sun, compressed into a tiny region. The evidence accumulated. Galaxy after galaxy showed the signature, a supermassive black hole at the core. Our Milky Way was no exception. In the 1990s, astronomers using infrared telescopes tracked stars orbiting near the galactic center. One star, designated S2, completes an orbit around Sagittarius A star every 16 years. Its orbit is highly elliptical. At closest approach, it whips past at nearly 8,000 kilometers per second, 3% the speed of light. And the only thing that could hold it in such an orbit is a supermassive black hole, 4.3 million solar masses, right there, at the heart of our galaxy. We now know that almost every large galaxy has one. The bigger the galaxy, the bigger the black hole. The relationship is remarkably tight, and it suggests something profound, that black holes and galaxies grow together, co-evolve, that you can't understand one without understanding the other. None of this was obvious before 3C273. Before quasars forced the issue, supermassive black holes were optional, speculative. After 3C273, they became essential, a core component of galaxy formation and evolution. And the field of black hole astrophysics, which barely existed in the early 60s, exploded. Papers, conferences, entire careers built around understanding these objects. But the legacy goes deeper. 3C273 didn't just teach us about black holes. It taught us how to use the universe itself as a laboratory. Quasars became tools, instruments for probing cosmology, testing relativity, measuring distances across billions of light years. One of the most elegant uses is as standard candles, or more accurately, standardizable candles. If you can determine a quasar's intrinsic brightness, either through its spectrum or through correlations between different properties, then by measuring how bright it appears, you can calculate its distance. This is the same principle used with supernovae and Cepheid variable stars. But quasars are far brighter, far more distant. They extend the cosmic distance ladder farther than any other single object type. In the late 20th century, astronomers used quasars to map the large-scale structure of the universe. By cataloging millions of quasars and plotting their positions in three-dimensional space corrected for redshift, they revealed the cosmic web, the filaments and voids, the scaffolding of dark matter on which galaxies hang. It's one of the most beautiful images in modern cosmology, and it wouldn't exist without quasars. Quasars also test general relativity in extreme regimes. Near a supermassive black hole, gravity is so strong that space-time curvature becomes dramatic. Time slows, light bends, orbits precess, and quasars, by being both bright and variable, allow us to observe these effects directly. When material in the accretion disk moves closer to the black hole, it speeds up. The Doppler shift changes. The light spectrum shifts. By measuring those shifts, astronomers can map the gravitational field around the black hole. They can test whether Einstein's equations still hold in such extreme conditions. So far, they do. Relativity passes every test. But the fact that we can test it, that we can probe gravity in regimes billions of times stronger than anything achievable in a laboratory, is remarkable. And quasars make it possible. Then there's the role quasars played in understanding the early universe. Before quasars, our view of cosmic history was limited. We could see nearby galaxies' relatively recent snapshots. We could theorize about the past, model it, extrapolate backward. But we couldn't observe it directly. Quasars changed that. Their brightness made them visible across vast distances, across vast stretches of time. Suddenly we had windows into the universe as it was 10 billion years ago, 12 billion, 13 billion. And what we saw was surprising. The early universe wasn't quiet. It was violent, energetic. Quasars were everywhere. Black holes were feeding voraciously. Star formation was rampant. Galaxies were colliding and merging at rates far higher than today. The cosmos was young, wild, chaotic. That knowledge reshaped cosmology. It forced us to confront the fact that the universe has aged, that it was once fundamentally different, not just smaller and denser, but more active, more turbulent. And quasars were the key evidence, the smoking gun. Have you ever thought about how fragile discovery is? How easily 3C273 could have been missed if radio astronomy hadn't developed when it did, if the third Cambridge catalog hadn't been compiled, if the moon hadn't occulted 3C273 in 1962. Giving Cyril Hazard the precise position, if Martin Schmidt had been too busy that week to examine the spectrum, the discovery might have been delayed. Years, decades, and all the science that followed, all the insights, all the applications, would have been delayed too. But it wasn't missed, because people were curious, because they built instruments to explore new wavelengths, because they followed up on anomalies instead of dismissing them, because they trusted the data even when it pointed to something strange. That's a lesson worth remembering. The history of science is full of accidental discoveries, serendipity. But serendipity only works if you're paying attention, if you're willing to investigate the unexpected, if you don't ignore the outlier because it doesn't fit your theory. 3C273 was an outlier, a faint blue dot that didn't behave like a star. And instead of dismissing it, astronomers leaned in. They looked closer, they measured more carefully. And they found something that rewrote textbooks. The scientists involved deserve recognition. Martin Schmidt, of course. His name is forever linked to the discovery, but also Cyril Hazard, who provided the crucial position measurement, Alan Sandage, who identified other quasars and helped build the early catalog, Jesse Greenstein and Thomas Matthews, who studied 3C48 and confirmed it was similar to 3C273, and dozens of others, theorists who modeled black hole accretion, observers who tracked quasar variability, engineers who built better telescopes and detectors. Science is collaborative, cumulative. One discovery builds on another. One measurement enables the next. And 3C273 was a foundation stone, a cornerstone. Everything that came after, from the discovery of millions of quasars to the imaging of black hole shadows with the Event Horizon Telescope, traces its lineage back to that first quasar, that first moment of realization in 1963, when Schmidt understood what he was seeing. It's also worth noting what 3C273 taught us about humility, about the limits of human intuition. Before the discovery, no one predicted quasars. No one imagined that objects so bright and so distant could exist. It was outside the realm of expectation. And that's a reminder that the universe is under no obligation to match our assumptions. It is what it is. And our job as scientists, as curious beings, is to observe it honestly, to measure carefully, to follow the evidence wherever it leads, even when it leads somewhere uncomfortable. Quasars were uncomfortable. They challenged existing models. They required accepting that black holes, which many physicists doubted, were not only real, but central to galactic evolution. They forced cosmologists to rethink the history of the universe. They made theorists work harder, build better models, confront gaps in their understanding. And that's good. That's how science progresses, not by confirming what we already believe, but by encountering things that don't fit, things that demand explanation, things that force us to expand our framework. 3C273 expanded the framework of astronomy more than almost any other single object. It opened a new field. It introduced new physics. It connected black holes, galaxies, and cosmology in ways no one had anticipated. And it did so quietly, without fanfare, just a faint blue dot in a photograph, a spectrum that didn't quite make sense, a patient astronomer willing to stare at it until understanding clicked. That's the poetry of it. That's something so visually unremarkable, a tiny point of light. It could be so profoundly important, could teach us so much, could change everything. And the legacy continues. Quasar research is still vibrant, still producing discoveries. The James Webb Space Telescope is finding quasars from the universe's first billion years. Radio telescopes are mapping quasar jets in unprecedented detail. Gravitational wave detectors might soon catch the mergers of supermassive black holes, the events that create the brightest quasars. The story that began with 3C273 is far from over, but every chapter, every new discovery, every refined model carries the echo of that first quasar, the one that started it all, the one that showed us the universe was stranger and more magnificent than we imagined. And in a way, that's the most profound legacy, not the specific facts about black holes or redshifts or accretion disks, but the reminder that the universe is knowable, that with patience, with careful observation, with the courage to question, and the humility to listen, we can uncover its secrets. We can understand things that seem impossible. We can turn faint dots of light into stories, into science, into wonder. That's what 3C273 represents. A victory of curiosity, a triumph of human ingenuity, a monument to the idea that the cosmos, vast and ancient and strange, is within our reach, not physically. We'll never travel to 3C273. We'll never visit its black hole or touch its accretion disk. But intellectually, scientifically, we can grasp it. We can know it. We can make it part of our story. And that knowledge, that understanding, becomes part of who we are, part of how we see ourselves. Small, yes. Brief, yes. But connected. Participants in something vast. Witnesses to wonders. 3C273 gave us that, and for that it will be remembered, not just as the first quasar, but as the doorway, the threshold, the moment we stepped through and saw the universe as it truly is. But beyond the science, beyond the discoveries and the legacy, there's something else, something quieter, something personal. And that's where we turn now, as this journey draws toward its close. We began with a question, a simple one. What could shine brighter than 1,000,000,000,000 suns from a region smaller than a solar system? And over the course of this quiet night, we found our answer. Not just in facts and figures, not just in redshifts and accretion disks, but in something deeper, in the realization that the universe speaks to us, in light, in time, in mysteries waiting patiently to be unraveled. 3C273 is still out there, right now, this very moment, still feeding, still shining, still launching its jet across hundreds of thousands of light years. The photons it emitted today won't reach Earth for another 2.4 billion years. By then, our sun will be nearing the end of its life. The oceans might be gone. Humanity, if we still exist, will be unrecognizable. But those photons will keep traveling, patient, unstoppable, carrying a message we'll never receive. And the photons arriving tonight. They left when Earth was young, when life was simple, when the story of everything we know was just beginning. They crossed a quarter of the observable universe to get here, survived the expansion of space, dodged dust clouds and gas, persisted against impossible odds. And they ended their journey by landing on a telescope mirror, by being counted, studied, understood. There's something profoundly moving about that, about the fact that we brief sparks of consciousness on a small planet can reach across billions of years and touch something so distant. We can't visit 3C273. We can't send probes there. We can't even see it with our naked eyes. But we can know it. We can understand its black hole, its jet, its history. We can make it part of our story. And in doing so, we connect ourselves to the cosmos in a way that transcends biology, transcends time. We become witnesses, participants, not just observers of the universe, but part of its unfolding narrative. Think about what we've learned, not just tonight, but over the decades since Martin Schmidt first saw that spectrum and realized what it meant. We've learned that black holes are real, that they sit at the hearts of galaxies, that they're not cosmic drains, but cosmic engines capable of producing more energy than anything else in nature. We've learned that the universe was once wilder, brighter, more violent than it is today, that quasars dominated the sky when the cosmos was young, that galaxies evolve, that they have phases that they grow and quiet and sometimes flare back to life. We've learned that distance is time, that looking far is looking back, that the night sky is not a snapshot, but a history book, each page written in light. And we've learned that the most important discoveries often come from the most unexpected places, from faint dots on photographic plates, from anomalies that don't quite fit, from scientists willing to question, to measure, to trust the data, even when it points somewhere strange. 3C273 taught us all of that, and more. It taught us humility, the recognition that the universe is far stranger than we imagined, that our intuitions honed by life on a single planet orbiting a single star are poor guides to cosmic extremes, that we must listen to nature, observe carefully, follow the evidence, even when it leads to black holes, even when it leads to objects that shouldn't exist. But it also taught us hope. Because if we can understand something as alien and distant as 3C273, if we can decode its light and reconstruct its history and grasp the physics that powers it, then what else might we understand? What other mysteries might yield to patience and curiosity and careful measurement? The universe is vast, incomprehensibly vast, filled with wonders we haven't found yet, phenomena we haven't named, questions we haven't thought to ask. And somewhere out there in the deep dark, another beacon is shining, another mystery is waiting, Another discovery will rewrite what we thought we knew. That's the beauty of science. It's never finished. Every answer opens new questions. Every discovery reveals new horizons. 3C273 was the first quasar. But it won't be the last story we tell about the universe. It's just one chapter, one moment in an ongoing conversation between humanity and the cosmos. And you're part of that conversation by listening, by wondering, by letting yourself feel the weight of 2.4 billion years, the enormity of 886 million solar masses, the impossibility of light traveling so far for so long just to reach us. Have you ever stood under a truly dark sky and felt small? Felt the vastness press down on you, not as a burden, but as a kind of awe? That's what 3C273 offers. Not just knowledge, but perspective. A reminder that we are tiny, brief, fragile, and yet somehow capable of reaching across the universe and understanding it. That's the paradox of being human. We're insignificant on cosmic scales. A few billion people on a single planet in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies. We live for decades, maybe a century if we're lucky. The universe has been around for 13.8 billion years. We're a flicker, a heartbeat, barely noticeable. And yet, we notice. We measure. We calculate. We build telescopes and write equations and ask why. We take the light from a quasar 2.4 billion light years away and turn it into understanding, into wonder, into stories we tell on quiet nights to help each other see the universe more clearly. That's not insignificant. That's remarkable. So, here we are. At the end of this journey, we've traveled from a faint blue dot in a photograph to the edge of a supermassive black hole. From the 1960s, when quasars were first discovered, to today, when they're standard tools in cosmology. From confusion and mystery to understanding and awe. 3C273 is still shining, still out there, still waiting for anyone curious enough to look. And maybe that's the most important lesson, that the universe is always there, always waiting, always ready to reveal itself to those willing to see. You don't need a PhD to appreciate it. You don't need a telescope. You just need curiosity, the willingness to ask questions, the patience to sit with answers that take time to understand, the humility to accept that some things are bigger than you, and the courage to look anyway. Because that's what we've done tonight. We've looked, we've listened, we've let the light from 3C273 ancient and patient tell us its story, and in doing so, we've connected ourselves to something vast, something beautiful, something that will outlive us by billions of years, but is for this moment ours to know. Science is often described as cold, impersonal, a collection of facts and formulas. But that's not what it is, not really. Science is a conversation between us and the universe, between curiosity and mystery, between the light that travels and the eyes that see it. And 3C273, for all its violence and brightness and strangeness, is part of that conversation. A voice from the deep past, speaking to us, waiting for us to listen. And we have listened. We've heard its story. We've understood as much as we can what it is and how it works and why it matters. And in understanding, we've become part of something larger, part of the long, slow effort of humanity to know the cosmos, to make sense of the night sky, to turn distant lights into knowledge. That effort continues. It will continue long after we're gone. New telescopes will be built. New quasars will be found. New mysteries will emerge. And people like you, people willing to spend a quiet night listening to stories about the universe, will keep the conversation alive. Thank you for being here, for drifting with me through the story of 3C273, for letting your mind stretch across billions of light years, for sitting with the wonder and the strangeness and the beauty of it all. The universe is still out there, still shining, still full of stories waiting to be told. And there are more journeys ahead, more quiet nights, more mysteries to explore. So, rest now. Let the weight of cosmic time settle softly. Let the light from distant quasars remind you that we are small, yes, but connected, part of something infinite. Sleep well, dream gently, and when you're ready, we'll drift again, toward another corner of the cosmos, another story written in starlight, another wonder waiting in the dark. Until then, look up. Sometimes, when the sky is clear, and remember that the light you see even from the faintest star has traveled so far just to reach you. And that's a kind of miracle. Quiet, patient, eternal. Good night.